In this paper, we explore the problem of event-based Meshflow estimation, a novel task of predicting a spatially smooth sparse motion field from event cameras. The optical flow is the movement of all pixels on the picture plane over time. Pixel-level optical flow has spatial information redundancy and is computationally costly since neighboring pixel movements are very comparable. Meshflow is a spatially smooth sparse motion field that only records motion vectors at mesh vertices. It can accommodate non-rigid global motions while reducing computational costs and redundancy in motion information. So Meshflow is widely applied in various vision applications, such as image alignment, video stabilization, and HDR imaging. However, RGB images often lose fine image texture details and suffer motion blurs under extreme scenes, making motion estimation challenging. While event cameras are well suited for motion estimation under extreme scenes with its high temporal resolution and high dynamic range. To the best of our knowledge, none of the event-based datasets involve the estimation of Meshflow. Existing event flow datasets, such as MVSEC and DSEC, can't provide high-quality Meshflow labels extracting form optical flow. Our pipeline for dataset generation is: camera trajectories and dynamic objects are randomly placed in 3D virtual scenes to render high frame rate videos and optical flow labels. Then events are generated from videos and Meshflow labels are extracted from optical flow. The methods of extracting Meshflow is: propagate the median movements in the neighborhood to the mesh vertices and filter outliers using median filters. We build the first event-based Meshflow dataset, named as HREM, superior in the high-resolution dynamic scenes, complex motion patterns, and physically accurate events in Meshflow label. We make ablation experiment on HREM dataset. Meshflow achieves image alignment comparable to optical flow, but downsampling flow twists the shape of objects. The second part of our work is to build an efficient event-based Meshflow network, called EMFlow. It is designed with minimal computational overhead by employing the lightweight encoder, building cost volume with dilated feature correlation, and using group shuffle convolutions during decoding. Our EMFlow performs well across scenes and speeds, achieving SOTA on average EPE metrics. Besides, EMFlow's inference is fast, about 39 times faster compared to the well-performing flowformer. EMFlow's subjective results are also most similar to Meshflow GT. Moreover, EMFlow's estimation for image alignment have minimal shakes in contrast to other methods. The third part of our work is upgrading EMFlow to EMFlow Plus 4 optical flow estimation. EMFlow Plus employs the coarse to fine residual approach to progressively refine the flow prediction, together with CDC module to enhance motion boundary details during flow upsampling. CDC module consists of two branches. One is the self-corrector. It outputs the correction flow to correct the error region, and the confidence map to retain corrected regions with high confidence. The another is the self-correlation. It outputs the attention weight to focus on the error region and supplements the flow values of pixels which is warped by the corrected flow. Our EMFlow Plus achieves the SOTA performances on DSEC dataset at high inference speed. And ablation experiments have validated the effectiveness of the CDC. Experiments also have shown that events over RGB images in extreme scenes and event Meshflow networks are the most accurate and the fastest. In conclusion, we developed the first event-based Meshflow dataset, then give an efficient event-based Meshflow network, called EMFlow. Finally propose a CDC module to upgrade EMFlow as EMFlow Plus 4 optical flow estimation. Thanks for your listening.